Oh, see if it's just in here. There we go. All right.
Hello, sir.
Hello, how are you doing?
Yeah, thanks.
All right. So, I was gonna wait for a few more people to join us, but I'm gonna try and do more of these interactive lessons, so it's not just videos anymore.
Okay.
Just to make it so that we can talk a little bit, and then if you can't make it or you can't get the link to work or whatever happens, I'm always gonna, after the class, upload the videos online.
Okay.
So that way you can watch them again if you want to or anything like that.
Okay.
So that's the plan for today. Oh, we got another one. Ryan. Go on, Ryan. So let me go ahead. I'm going to...
Do we need the books?
Yes. Yes. Follow along with your book is probably the easiest thing. Just because the book's got all the pictures and everything like that with it. So let me go grab my copy real quick.
Okay. Give a minute to bring my books.
Yeah, yeah. The book's the best thing to bring though, for sure. It'll help you out in the long run. So.
Okay.
As long as you're reading Unit 31, that's the biggest thing. Oh, got a phone call. Let's see. Hello? Yes.
Hello. Oh.
Yeah. Oh, okay. I thought you said you were filling that out. You just needed our information, but okay, I'll fill out that blue one then. Yeah. Yeah. Let me finish my afternoon class, and I'll get on with that because I'm right now in the middle of a Zoom with him. All right. Okay. Yeah, I gotcha. Sorry about that. Had to go get my textbook, and then oh, and my dog is now got in the way. Oh, of course. Thank you, Petunia. It's not where my feet were like 2 seconds ago or anything. She is not a very well behaved dog sometimes. All right. Okay, so Duante. All right, so Unit 31 is what we're going to be in still. That's all we're going to be going over for this class. next couple of weeks and everything like that. Yesterday, I did get an email from the dean and the president saying that they're hoping we can be back to normal in about 30 days. But again, that's all up in the air. I don't know what's going to happen with it, so we'll see. But we'll go ahead. What I'd like to do for this class, and I'll send out this information again as we start doing these more often. I'd like to have it where we can be interactive and without, interrupting or going crazy. So if y'all all look on your computers, if you've got the computer version of, I'll show you my screen. If you've got the computer version of Zoom and, ooh, crap. All right. All right. This would be at the bottom of your screen, the same kind of thing right here. How do I do this? On the shared screen. Oh, crap. Okay. Apparently I can't do it on the shared screen. Okay, well, that's weird. All right. But if you got it, there should be a section that says reactions, or if you have the mobile app, if you swipe right, you'll see a thing that looks like hands clapping, or it looks like a thumbs up. And what I want you to do is, instead of just interjecting when I'm doing the lesson and everything like that, just all you got to do is click on either the hand clapping or the thumb up, and then I'm going to stop what I'm doing, and I'll, I'll unmute you or you unmute yourself, and we'll do a quick discussion if you got a question or whatever. The other option is we do have, I think there's a chat with this and everything. So if you want to just type into the chat, what is something about, what kind of pilot, you can just click into the chat and just ask questions in the chat. So that way, it can go seamlessly and I can type back in, or I'll just answer audibly, say, oh, you asked this and here's the answer. So that's what I'm going to try and be doing with this. So it's just a matter of getting it timed out right, getting it to where it's normal and functional for us. Right now, this Zoom meeting is set for like 30 minutes. I don't know if it'll cut out at 2 o'clock or not. But next one we have will be at 2:30. And that'll go till at least 3:10. Again, it just matters as far as what happens with the programs and everything on the computer. But I'm just going to try to make it so that we have time to discuss furnaces and not just, oh, here's Mr. Williams just talking for 40 minutes or 2 hours, because that, what was it, 2 days ago or whatever, when I did that recording and those videos and everything, I hated that. I was not a fan. I thought it'd be easier just because, you guys could watch it whenever, but then I realized I could just do it live, record it, and then you could still watch it whenever. So I decided we're just going to do that. It's a lot easier, and it lets you guys get more information. The 1:30 time as opposed to 1:15, the reason I'm doing that is just to make it so that if anything right at 1:15 you got to take care of, or try getting in. I'm going to try to have the link ready, links ready ahead of time from now on, since we're going to be doing this more often. And that way you guys can, get right into it, and you don't have to wait or anything like that. So still trying to figure it out. But once I get it all situated, once I figure out how to use the Zoom the best way possible, again, suggestions. Tell me what you think would be better, what would work better, what might not. You can always email or call or text me, or anything like that. Because last night I had it where I had a class and I did the recordings for them, and they were not happy about it. They wanted to do something different. They wanted more discussion, and I was like, yeah, that makes sense. So that's what I'm going to be trying to do in the meantime. So for us as a class, we're still going to be meeting 3 times a week. All the other classes only meet twice, but we're only meeting for 80 minutes each time, so 2 40-minute sessions is all it should be. Some of that time in that 80-minute session might still be pre-recorded videos from YouTube, just because we can talk about a lot of stuff, but there's also going to be some extra time set aside. Or, I mean, if we talk for 80 minutes, we talk for 80 minutes. But I'll also send you guys some YouTube videos most days to help give you more information and show you the components. Because the one problem I've got is while I'm working from home, I cannot show you guys components and parts and different things like that. I've got no way to, get to your furnace or anything. So that's all. I just wanted to get that whole message out there before we started. So we're just going to be doing these more often. That way you all can follow along, ask questions as needed. I'm going to go ahead and get started on screen sharing. So, okay, cool. And let's go. The currents. There we go. Okay. So, our objectives for the lesson today, what we're looking into, is going to be high efficiency furnaces mostly, and what a furnace efficiency rating is all about. Basically, what does that mean? How do you have it where you're going to have these different components and parts? What makes a high efficiency furnace, and what's allowing it to get higher efficiency? What's the difference there? And how can you tell what's the standard? There's got to be some standard of efficiency. For cars, we all know the standard for efficiency is typically going to be, your miles per gallon. That's pretty typical. For appliances in a home, it might be kilowatt hours annually. For something like a dryer or a washing machine, you'll see those Energy Star ratings on all different appliances. These will be a good basis for those different applications. But for heating and air conditioning appliances, you've got a different set of ratings and a different set of rules. All right, for miles per gallon, that makes sense. What's the purpose of a car? It's to get you to go from point A to point B, and it's going to go so many miles. All right, and then if you've got what's the fuel source? Okay, gallons of gas. So how many miles are we going to get out of this 1 gallon of gas? Because that's the typical unit that it's sold in. If it's if it's a car sold over in some other foreign countries, they might do it where the MPG is not MPG. It might be kilometers per liter, but it's still the same concept. It's a measurement of how much of my energy or my fuel source am I consuming in order to get my job done. So for us, what we're going to talk about later today is going to be the AFU rating, and we'll go into detail about that. So high efficiency gas furnaces. You guys have already seen these in the classroom. When we took out our 2 different heat exchangers, we had it where there was the one that only had the 1 set of tubes, and that was your single stage low efficiency gas furnace. And then you had it where there was the one where it had the tubes, and it went down into that finned tubed system where it had all those little pieces of metal that were just like spinning around inside of it, kind of thing, that weird bent up little aerator, kind of that disturber thing. That's going to be the big difference as far as mechanically, what's the difference between a low efficiency and a high efficiency furnace. The big thing with a high efficiency gas furnace is it reduces outdoor air infiltration and room depressurization. The reason for this is, all right, if you have a house and you're heating up with a gas furnace, all right, you got to have 3 things for combustion every time. You guys know this at this point: fuel, oxygen, and heat. All right, always remember we got fuel, oxygen, and heat. So as long as we got fuel, oxygen, and heat, we're going to have combustion. The problem with a gas furnace is when it's operating. All right, where's that air coming from for that combustion? Where's that oxygen coming from? It's coming from the air inside of the house. So wait a minute, aren't we trying to condition that air to be a specific temperature and not, just throw it out of the house? Because what happens is if we have it where the combustion air was, because air is going to recirculate out and throughout a house and everything like that, it's going to get back to that mechanical room where that furnace is located. And when it gets back to the mechanical room where the furnace is located, that's when you can see, you're going to have that conditioned air is in that mechanical room most of the time. It's going to have some ductwork in there so that it doesn't, we don't, you're probably going to have some plumbing down there so you don't freeze your pipes, so you don't have anything, ice up or have any issues in that mechanical room. You're going to have the air conditioned, whether it's cooled off or whether it's heated up. Now, it might not be as comfortable as, the bedroom or the kitchen. It's not a major priority. But you have it where when it's taking in that conditioned air as part of its combustion process, it's literally negating the work it just did, depending on where it's located again. So typically for a gas furnace, you're not going to have it where it's located in an area that's open to, let's say the whole basement. An unfinished basement with a gas furnace is going to have that gas furnace enclosed in a smaller space so that it doesn't eat up all the air in that basement and eats up all that energy that was used to heat up the air in that basement. Or if you have it where I've seen it in finished basements. A lot of times you'll see furnaces down there, and they're not going to be really in just the hallway or just sitting in the middle of the room or anything like that. They're not going to run. They're going to be off in their own little area. They're going to have some sort of door or a sliding cover or something like that that's going to separate the combustion air that they use from the air in the rest of the building, so that we can use as little conditioned air as possible for our combustion process. That's the whole idea behind it. Another problem you can have is backdrafting. And you can have it where there can be pressure problems with the air in a home if you have combustion going on a lot in the home. So, for example, if you go out to the Midwest, or if you go to a lot of older homes that will have gas lines hooked up, not just for a water heater, not just for a furnace, not just for a stove, but also for something like a dryer, right? So if you go in and you have it where you've got an old building and they've got a gas furnace, and they've got a gas water heater and a gas dryer, and they're all located in the same exact utility room, all three together. Well, all three are going to need the same thing. They're all going to need fuel, so they're all got a gas line to them. They've all going to need heat, so they've got different kinds of igniters, and then they're all going to need oxygen. Oh, well, they got independent gas and they've got independent heat. What they don't have is independent oxygen and independent air for combustion. A high efficiency gas furnace literally pipes in air from outside of the building, outside of the structure, brings it in for combustion, and uses that outside air as its source of combustion. It doesn't rely on any air from inside of the room. Can it do that? Yes. Ideally, for that high efficiency system to reach the efficiency level that it's rated for, it needs to bring in outside air down into our burners, and that way we've got fresh air from outside being used as a combustion process and everything like that. And then when it goes back out of the house with a high efficiency furnace, we're getting most of the heat off of it, so it comes out slightly warmer air. So we're not wasting all that energy. If we were to do that with an old mid-efficiency furnace, if you were to pipe in outside air for that, you would still see a really high waste level, because it doesn't hold on to nearly as much heat. So it would be heating up that outside air very, very much, and then throwing it outside of the house still very, very hot. And you'd start heating the outdoors almost, is what you'd be doing. Not to an insane or true level of like actually, oh, your house outside is like radiating heat and your lawn's like melted while your neighbors, have snow everywhere. It's not going to be that bad, but you do have it where uh, having that outside air come in for combustion is really, really good to help with room depressurization. Um, Outdoor air infiltration is another issue, but that's typically solved more or less with the making sure that your flue gases are flue piping is well insulated and sealed, and that you have a good seal in the building as far as windows and insulation. I was just talking to my buddy Eric about this the other day. He's got a house that I always try to help him out with, and he was asking me about, he wanted to go with a tankless water heater because I've been talking his ear off about it, and because he has a like 12-year-old water heater. That thing is no, not 12, 18, 18. It's an 18-year-old water heater. It's going to go any day because I know he hasn't had any maintenance on it because he told me that. He's like, yeah, no, we've never had anyone come out to look at it. I'm like, oh, great. So I told him, I was like, look, when it goes, let me know, and we'll just install a tankless one. And his whole question for me is, more or less about, well, is it really going to save that much? What's the efficiency level? What's going to be? And, then I started telling him, because he's got a 2002, that's 18 years, 2002 gas water heater. He's got a 1996 gas furnace and a 1998 air conditioner. All right. His system's old. So he knows, I've told him now, I'm like, look, you need to keep in mind that in the future, in the near future, you're going to have to get replacement for all of these major mechanical parts in your home. When you do that, go with high efficiency. Because currently what he's doing is he's probably at about 75% efficiency for all of his systems. If he upgrades to 90% efficiency for it, he is now saving over 50%, close to 60% on his gas bill annually compared to what he was spending previously. And that's the whole difference you can have. It's ridiculous the difference between old systems and new systems. Old system, 80% efficiency was considered great, and now it's 90 is considered great. Well, that's half your gas right there. That's a 50% of your bill sliced in half, just because the new systems happen to be that much more efficient just by default. Just had to check the time. And I thought my phone was going off too, so that's all good. So multiple heat exchangers, flue gas condensate disposal systems, induced or forced power drafted venting systems. Nowadays, you are not going to see any gas furnaces installed that do not have some sort of induced or forced draft system for their flue gases. Natural draft is just so inefficient. It's rarely used except for maybe some boilers. Boilers are the one where natural draft is used sometimes because it's a little different. I'd have to go into a whole thing explaining why natural draft is good for a boiler but not for a gas furnace. But for a gas furnace, the forced draft and the forced ventilation makes it so that we have, yes, another motor. So we've got now an inducer draft motor moving exhaust gases, but at the same time, we're also going to have it where we've got more control and more safety over the burning of our fossil fuels, the burning of our natural gas and everything like that, to make sure that all those flue gases are exiting the building. They're not just exiting on their own with a natural draft, they're being forced through ventilation, through our flue piping with our draft motor and everything like that. So the easiest way to tell the difference always between a high efficiency and a low efficiency gas furnace is looking at the flue piping. You can also tell the age of the system typically this way. I'm going to send out a video later today for you guys that'll explain different types of flue piping that we're seeing in the industry, what used to be common, what came in between, and now what the new stuff is. Old school was a stuff called C-vent. It was very thin metal. It was one wall, and that's all it was, just one thin wall of metal all the way around for that ventilation, and it would go out, and that would carry out your flue gases, no problem. That was used on coal-fired, oil, gas, all those fuel systems for boilers, for not for air conditioners, obviously, but for boilers and for furnaces. That's what you had used for your ventilation for years and years and years and years. About the mid 80s, they started using what was called B venting. And B vent is pretty popular. It's a little bit safer. All right. So instead of being one wall of a pipe, and everything like that, instead we've got it where it's going to be two. You're going to have an inner and an outer pipe, basically. You'll have the inner ring will actually be carrying the gases and everything like that, while the outer ring is just there to protect it and make sure that it's actually able to exit out of the building safely. And B venting is still very popular. That's what, when we see metal flue piping, majority of the time it's going to be B vent. C vent is not used anymore. I've seen it before. I've come across it and I've repaired it still, but it's not anymore in new systems. It's older systems. The nice thing about C venting compared to B venting is it's real cheap. Does not cost a lot. B venting can get a little expensive, especially when you're working with large lengths or you're taking a lot of 90s. You take a lot of turns in your venting as it goes out of the building. It's doot, 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 all these little steps up. That is actually going to cause a problem. You want to have your flue piping to be as straight as possible out of the building so that the heat can rise quickly, and the less bends, the less points you have for condensate to collect. So if the flue gases cool off and condensate collects in that flue piping, all right, that condensate should just run back down to the bottom and fall out in the floor or something like that if it's going to go anywhere. Or should basically be right there by our furnaces where it's typically going to be seen. But if we have a lot of 90s, if we have a lot of turns that it takes as it goes out of the building, each one of those little turns is a spot where that water can just pool and collect. And this is some nasty water filled with acid that's going to eat through our metal, and it will destroy our flue gas piping. I've come across flue piping before where literally you put your hands on it and it disintegrates almost. You just quick little let me see how it's doing. And then just my finger just goes right through the metal. This thumb goes through the metal. I'm like, oh, well, that's not even holding up to like a pinch, the slightest little pinch and it's punctured, falling apart, totally rusted out. This is why we got to have proper ventilation and proper sized piping for our ventilation. So the new stuff nowadays is HPVC. That's the plastic piping you've seen in the lab before. That is the most common for modern systems because it makes the most sense. It's low. It can handle low temperature flue gases. It's cheap. It's accessible, and it doesn't look ugly. It's going to last a lot longer than metal. It's plastic. It takes a long time to break down plastic. The ocean knows plenty about that. It's just one of those things that it's really durable. So it's, again, another way that we have for ventilation, another source of ventilation is going to be that. So, all right. So when it's talking about this, all right, if you guys look in your books, let me see what page it was. I had it just a minute ago. There we go. So page 869, all right. So operate below the dew point temperature of the combustion gases, all right. As XX air increases, the DPT, or dew point temperature, increases. So basically what it's talking about is the flue gases, I just said, we don't want them condensing, all right, except for in a high efficiency furnace. Because of that plastic, because we're operating at that lower temperature with our flue gas, and we know condensate's going to happen, with old inefficient systems, they prevented flue gases from condensing. That was the whole point. Make sure that those flue gases don't cool off, get them out of the building while they're still roaring, ripping hot. You cannot have it turn back into water. With the modern systems, we finally figured out a safe way to get rid of that water, to get rid of that condensate without damaging our system and without causing mechanical issues further down the line, or causing it where we have to do repair after repair after repair, basically. So the main thing with the DPT and with the dew point temperature and everything like that to keep in mind is just to make sure that that condensate line, because that's where that condensate, just like any other, is going to go down the condensate line, and you want to make sure that that line is clear. The last thing you want to have happen is a high efficiency furnace operating normally and the condensate line backs up and now someone's out of heat because a line with water in it is now backed up and now they're without heat. So what happens to that water line when it doesn't have heat in the building? If it's left for an extended period of time, let's say someone's on vacation, let's say someone's out of town, and they don't know that the furnace isn't working, and they come home and it's been almost freezing temperatures or freezing temperatures in the house the whole time, their pipes are going to burst, right? Not just the ones that's at a condensate line, but their pressurized water pipes in their home, that it can be a major problem. So we want to make sure we're always operating, always have where our temperature is getting up there, and then we have it where, you know, it'll drop back down. All right, this right here is what separates high efficiency, mid efficiency, and low efficiency systems. Is the efficiency rating. Yeah, the annual fuel utilization efficiency rating, or AFU, because nobody says the full thing. Everyone just says what the AFU rating. This is the one that is easiest to compare for customers. And like I said before, it's just like if they're looking at miles per gallon. All right. Now, the AFU rating, how it's written, is a percentage. All right. Basically, it's going to let them know what percentage of the fuel am I burning that's going to be okay, there we go. What percentage of the fuel that I'm burning is actually going to be going towards the heating of my structure? And what percentage of the fuel is going to go just right out the flue pipe, right outside the building, is not going to affect our heating ability whatsoever? That's what that percentage rating is all about. So high efficiency systems are typically starting at about 90% efficiency. But again, it just depends on, who's going to define what's high, what's mid, what's low. Your book has it on 872. Page 872 has got a great little bullet point list, basically explaining the difference between conventional or low efficiency systems, mid efficiency, and high efficiency. You're seeing it more and more nowadays. The reasons why we have to go over high efficiency furnaces, the reason why we have to talk about efficiency ratings, is because towns, cities, counties, states, federal government, anyone who's got a say in how buildings are built, right, which is every stage of government's got that. We've got it where federal, you got housing and urban development, all the way down to the local city board and council that decides on how gas lines are going to be run into a building or something like that, or safety codes based on a statewide level ordinance or something like that. So this is becoming more and more popularized. All right, EPA got founded back in like the 1970s. It's been working hard since then to try and make it so that we are protecting the environment and that we're using our fuel sources efficiently. That's a way we can protect the environment. If I just had it where I was sitting outside and I didn't, literally sitting outside on just like a concrete patio or something like that. No, just sitting on my chair. If I was just burning a propane tank openly, let's say I had a little burner attached to it or something like that, and that's how I was heating, that would be an extremely horrible way to use my fuel. That's a terrible, terrible way to get that done. Not to say that people were doing that kind of level of inefficiency before, but the EPA and the government basically strong arm and allow for us to make these radical shifts faster than what we do on our own pace most of the time. You know, it's why you have it where MPG keeps going up and up and up every year as far as a minimum level for cars, because trying to use gas better. Natural gas is another big thing. You know, when we have it where we're talking about oil production and we're talking about fuel production, natural gas and oil are usually right there side by side, all over Texas, all over South Dakota, all over the country. You've got it where you've got natural gas pockets, you've got oil pockets, and those two fossil fuels are very precious resources, and we want to use them efficiently. You know, if we've got to use them for, already we're going to be using them for, let's say, cooking or heating our water, or drying our clothes, but we want to have it where we can heat it up, you know, and not waste a bunch of fuel while we're doing it. So that's why we've got these different ratings. They're going to get more and more precise, and the government's just going to, you know, crack down. The big thing is, a lot of houses nowadays are finally getting to the point where their old, low efficiency, standard systems that, you know, were put in back in 1985 are starting to go finally. All right, now hold on, that's what? How many years? Like 30 some years, right? That's 35 years if that furnace was installed in 1985. All right, now that might be exaggerating a little bit. You might still see some 1995, 1999, still 20, 25 years. Those furnaces have been in that house. And now, after 20 or 25 years, it's either the heat exchanger starting to go, the maintenance is getting to be too much for them, whatever it might be. The customer's going to be looking to find a cheaper furnace, right, as far as operational cost. Now, when they make the jump from a standard efficiency system like that to a high efficiency unit, you're going to see it where their savings are not 50% of their bill, more like 66% or 2/3 of their bill is cut. They only pay 1/3 of what they used to for their natural gas heating. This is why we're having it where it's used more often, and why the government's saying you've got to do this, you've got to upgrade, you have to have that. And so when they go to look for a system, they're not going to find the same efficiency as when that house was built or when that furnace was put in available anymore. They're going to say, no, we can't put in that style anymore. That's not allowed. We have to put in a new high efficiency system. And actually, it's going to save you more money. It's only going to cost you maybe $500, $600 more than a mid efficiency system, you know? And it's like, wait, hold on, $500, $600, okay? And I pay it off, let's say 10 years, all right? So I got to save if it's $600 extra to get the high efficiency system. That's $60 a year. That's $5 a month. That's it. $5 more a month to get a high efficiency system, and you're going to save probably about $50 a month on your gas bill. Pretty easy math. You do that, and you've got it where now they're saving money, they're burning fuel efficiently, and they're not having, the whole thing cut out on them or anything like that. So I'll go ahead and call that for now. I got a phone call I got to answer real quick, and then we will pick back up at 1:30. Thank you, guys. Hello?